My talk is going to be machine learning of motor skills for robotics. And as I did my PhD very close to Hollywood, allow me to start it with a small movie. Most of you have seen these clips from the movie I, Robot. And I don't know for you, but this kind of movie brought me originally to robotics, since to really bring, well, can we create such kind of robots? And, well, how would we fulfill Hollywood's visions of, well, robots that can handle many tasks at once, have compliant but accurate control, and are capable of achieving in complex tasks in a cooperative manner, which is way beyond human programming? Well, classically, we have taken very, very smart students, PhD students, just like in this audience. We've taken lots of them, put them in a cellar, gave them pizza, Coca-Cola, and said, "Los geht's, guys, come on, let's get going." And a couple of months later, they would come back and they would have programmed a perfect task and it would fulfill our requirement. Just next year, we would have the same scenario. New batch of students, new task, hopefully new pizza and Coca-Cola, and we would have to start from the beginning. So clearly, we need something smarter, that our robots, well, learn and adapt to and refine to new situations and learn new skills. However, classical machine learning techniques, which would just take this as a monolithic block, a big bunch of data, would not, well, are not straightforward to apply here. Instead, what we really need are learning algorithms which are tuned for this scenario of motor control and motor skill learning in anthropomorphic robots. So the three key questions which we have to solve in order to create such task-adapt motor control systems is, first, how can we develop machine learning methods that can actually scale into this domain of robotics and which are sufficiently efficient, which can be applied in the context of learning of skills similar to a human, and finally, can we actually use both of these components in order to compose complex behavior? And of course, I'm only going to give you a small glimpse on this scenario. So we view the robot in this case as a system which maps state to action and which has a teacher which gives us a learning signal. And there's an feedback through the environment. We model the whole scenario in the form that we assume the system is in a state, and a next state is generated based on this state, and when this an action is generated based on this state, and this gives a next state and a reward. The environment is usually modeled as a probability distribution, and the teacher gives some kind of a feedback signal. Many classical methods now tried to use a deterministic set of rules in order to generate behavior, but this, we believe, is wrong. Instead, you should rather have stochasticity, which is kind of similar to chaos in the previous talk, in order to create a stochastic policy, which then gives you exploration. It makes algorithm design easy, and reduces the complexity. And sometimes even the optimal solution can be shown to be stochastic. When you apply this in a multi-step rule, what you obtain are trajectories, which are sequences of states and actions. You obtain a path distribution, which is a distribution over all states and actions, and you retrieve path rewards. The first problem which we need to deal is to learn from a teacher. Since most of us humans start either triggered by reflexes, or when we learn a new skill, we start from a teacher. Imitation learning is a relatively simple problem because here we would have a distribution of data and actions, like exhibit here in a simplified form with the actions here, the states here, and you would have to just reproduce this behavior with the path distribution, where you have the parameters theta to adapt your behavior. And this can be done quite efficiently by only adapting the model parameters to theta. And we can do this model-free, only based on our samples. The second thing which we need is reinforcement learning. Reinforcement learning means to self-improve. In this case, we only have the scores of the teacher, and we only generate behavior. And what you should see is that there is no notion of data in classical reinforcement learning. Instead, we run into a big problem there, since if there's no notion of data, you can only learn from in the direct vicinity of your actual data. If you have to believe you're staying on the policy, or you have to fudge some heuristics which eventually may converge, of course. So most of these things have problems when you do bigger steps with optimization bias. Now it turns out that when humans learn skills, they don't just jump greedily for something which would be explainable from their data, so not onto this optimization bias scenario, but much rather, they match the reward-weighted previous distribution of their states and actions. And this has been recognized very early, and I think Mark Toussaint's work also relates to that quite strongly, that that basically what we should do is we should rather match the reward-weighted previous policy. And, well, that you could simplify in the previous graph. We had now the states and action pairs again. Now this time we have some with low reward and some with high reward. If we were just matching the successes, we would much rather reproduce this kind of a distribution. The first scenario where we used this policy matching was in the DARPA Legged Locomotion program in the United States, where this year's the BDI Little Dog and 6 groups in the US, including MIT and Stanford, were given this little dog and had to run over rough terrain. This was the early stages where we didn't have that rough terrain, but nevertheless, with the limited capabilities of that robot, you would fall if you were accidentally stepping on an edge, on a too strong incline, or into a basin. So learning a foothold policy for a while gave us a nice edge there. Now, how do we formalize this? Well, when we formalize this, it becomes quite natural to reduce it onto reward-weighted imitation. We're just taking the path distribution which we've observed, multiplied by the rewards of the path, and match this with our new path distribution which we can generate. And this leads to EM-like algorithms which have the nice property of at least having the guarantee to go to a locally optimal solution. What's particularly cool is that when you look at the kind of data which you many times see in mechanical systems, where you have actually a noise which is Gaussian distributed. And the tremor in our muscles is actually kind of similar, only that the variance is then strength modulated. So if you do this assumption that you have Gaussian distributed exploration, you can reduce the whole story of reinforcement learning onto reward-weighted regression. And regression is one of the few things which we really, really know how to do well in machine learning. So reward-weighted regression becomes the key step here in our scenario. And this has led to a variety of algorithms which have turned out to be very efficient. The reward-weighted regression, which in the power algorithm, and well, most recently the cost-regularized kernel regression. We're now going to use this kind of algorithm to answer in this bigger framework the other two questions of how to learn elementary behaviors and reuse them with the context, and finally use it in this bigger scenario. So we want to now first figure out how can we learn basic skills similar to humans. And for that, we want to acquire and represent those skills using primitives, because A, humans seem to do it in many biological systems. B, because if you have a particular formulation for motor primitives, which allows us to reuse them in new situations in a more general way, which is invariant under certain hyperparameters or task parameters, and is well, very robust and superimposable. So we'll use this kind of representation, we will initialize it by imitation learning and improve it by trial and error on the real system. Now, I don't want you to go through these equations. What I want you to notice in these equations, which are the representation of our motor primitives, is that we have two kinds of parameters in here. One kind are the so-called shape parameters, which allow us to give a forehand or a backhand in a game of tennis a certain amount of shapes. The other one are task or hyperparameters, which allow us to reuse a forehand faster with a different goal in a very different scenario. So, what we need to learn are these kind of parameters, and the first kind we learn in order to acquire a task. The first, of course, we start with imitation learning as the more straightforward supervised learning problem. Just on the side, here again, we are reproducing states in certain actions. What you see here is a ball on a string scenario. So you have a rubber string, and you're now bouncing the ball. You're trying to bring in energy into the spring, and then it goes into a relatively regular limit cycle. This is not sped up. This is really this fast. And for us, it was actually kind of cool. So I have this one student who's a really good control engineer, and he said initially, learning stuff, screw it. I'll first hack it up. And he spent half a year in the lab trying to first get a perfect model, then do optimal control on it, then do all the other classical control textbooks things. And in the end, he had a barely working scenario, because of all the unmodeled nonlinearities, which are so hard to get in there. When we did imitation learning, we were basically done in a day. Now, of course, anybody of you who has learned tennis knows that imitation never suffices. When you play tennis, your teacher takes you by the hand, shows you there's a forehand, there's a backhand, and you feel everything aches, and it feels very awkward to do these moves. But nevertheless, you will not be able to hit back the balls from the ball gun right away. Instead, you need several hundreds of trials. So what you need is reinforcement learning for self-improvement. And what you see here is how a teacher takes the robot by the arm. And now in this case, our human teacher actually has a spike in there where he creates accelerations which our robot cannot reproduce that well. And what you see is that this actually has a drastic impact on the task. So, but what you could see also is it has learned one key component. It has to inject energy into the ball, with the result that now by trial and error, it can eject again and again more energy and figure out how to move the ball closer to the cup. It gets a reward based on the similarity between, based on the minimum distance where the ball passes the cup. And we usually get it in for the first time at around 40 to 45 trials. And we get it in all the time after about 90 trials. And we have obviously asked how does this compare to humans? And well, we did a study on different kids of different ages. And what we figured out is that 6-year-old kids don't manage to learn it at all. That 10 to 12-year-old kids learn it within 30 trials, so they are quite a tad better than our algorithm already. And grown-ups are really good. They can learn it within 3 trials, at least if the person has a fair amount of prior exposure to complex motor skills. And so what is interesting, nice, of course, is we can hit it into the ball all the time after 90 trials, which none of the humans would ever manage. Next part, of course, is that we want to take these primitives and we want to reuse them in slightly different behavior. And for that, let me quickly remind you, in this case, we assume we have learned the shape parameters of a behavior, and now we want to modulate them by learned task or hyperparameters. And we've done this in 2 scenarios. In both of these cases, in one case, we're throwing a ball which is just on a, kind of in a bowl, so that you don't have control over the timing of your release. In the other case, we have the hands of the Sarkos CBI robot, where we can determine exactly when to release the dart. In one case, we're now using this, we're telling it, throw to a particular spot on the dartboard, like if you're playing a dart game in a pub. In the other case, we're modulating it by telling it, well, you have to achieve on the long run a sum of 15 by throwing them in different things, and things can go wrong. In both of these cases, we can learn the supervisory policy by the cost-regularized kernel regression quite efficiently. Another scenario where we have used this modulation of hyperparameters is in the grasping scenario, where we use shape parameter vision descriptors in order to create the right shape parameters so that we are capable of generating quite a variety of different grasps. Now, what I've shown you so far is a certain amount of learning algorithms, which for imitation and reinforcement learning. I've also shown you of how we can learn basic behavior from imitation and reinforcement learning, and how to modulate them to different scenarios. Now, I'll take all of these three elements in the next case, and I'll put them together. And so we now reuse this whole architecture in one box I haven't talked about, of how we learn good models for execution. And we now learn first several motor primitives by imitation. Subsequently, we self-improve them on repetitive targets and generalize among the targets and hitting points. And this is still, to some extent, work in progress. Here you see demonstrations of hitting the ball, and here you see how the robot returns the balls. And what you see here is already the step after the reinforcement learning, since as it cannot create the same kind of accelerations as the human can, because we have these wonderful muscles which give us a spring damper property, which subsequently allows us to create really high accelerations. The robot actually has to be faster during the movement in order to have the right speed at the hitting point. Our next steps are to select among even more different kind of motor primitives, to learn the whole motor game where we now incorporate the human, predict what the human is doing, and use this in a bigger scenario. Well, with that, I'm at the conclusion. It's obviously not all table tennis when we're talking about robot skill learning, but we really do make contributions then also to core robotics. We do develop machine learning algorithms there, and we both take inspiration by modeling human movements and from behavioral data, as well as that some of our algorithms are now used in brain-robot interfaces for stroke patients as well. And while we are interested in all kinds of related things in robot skill learning, for example, tactile exploration, where a robot explores its environment, explores different surfaces and learns what surface corresponds to what kind of feeling of touch. With that, I'm at the conclusion. So I hope I've kind of made the case to you guys that motor skill learning is a promising new approach for learning the software of robotics, which, as we learned this morning, is something which still has to become cheap. We have efficient methods for imitation and reinforcement learning, at least for learning primitives. And, well, we get at the moment as far as table tennis, as basic, very, very basic table tennis. And I hope many other topics, as on the last slide, benefit from this work. More information can be found at robot-learning.de. And with that, I would like to thank you for your attention. These people all interact with me on this work.